Hello, I'm Michael Fowler from Virginia Tech. I'll be introducing our paper Constraint Action POMDPs for Multi-Agent Intelligent Knowledge Distribution. This basically answers the question of what information should be shared to whom and when in a multi-agent and collaborative environment. We do this through POMDP policy iteration with constraint optimization. The policy improvement is represented as a finite state controller, and we actually search inside the policy space for updating this finite state controller. The belief updates introduce new machine states, and then they are pruned to provide a new controller that is better or at least as good as the previous one. In constraint improvement, we basically do discrete optimization through a branch and bound technique. The basic idea behind this is to look at what machine state could we introduce that probably wasn't the dominant vector, but utilizes less resources while trying to stay within the initial optimal value function as much as possible. If you look to the bottom right, you can see that C1, when it comes to machine state 3, where machine state 3 dominates in the middle of the region, C1 dominates very close to the same as it, but it utilizes less resources. So by introducing that constraint into the finite state controller, we get something that utilizes less resources, hopefully getting us within the constraint satisfaction that we're looking for, while minimizing the impact we have on the overall value function. Now we evaluate the finite state controller through a Markov chain Monte Carlo. Basically, we randomly sample the finite state controller over and over until the MCMC algorithm actually gets a posterior distribution. In the formulation of the intelligent knowledge distribution, it's basically 3 drones that have heterogeneous sensor resources. And they've got to figure out what sensor information is more useful to which one of the other UAVs. The value of this information, or the rewards that drive the constrained action POMDP, are basically looking at the KL divergence between what the local beliefs are and what that agent believes the remote belief of the other agent is. As they collaborate more and more, those two will get close to each other. But as they spend less time collaborating, the relative entropy between the two becomes great enough the reward is driven up, and a communication is ensued between the two. When we looked at this, the optimal policy only met the constraint satisfaction 10% of the time. By introducing constraint states into it, we're able to get the constraint satisfaction to near 90 or greater than 90%, while still staying within 54% of the optimal value function. If you have any further questions, please come see me at the location below on the video's banner. Thank you.